Well, it's the title, the subject, the theme for this discussion is something which perhaps ill-advisedly gave as a title to a talk that I gave some years ago, and that's been written up. So I will confine myself to selecting 2 or 3 points that, out of several that I talked about in that long article. Of course, the issue is what is meant by Indian mathematics. Mathematics, we know, is a very universal discipline. The substance cannot change. The theorem of the diagonal is the same as the theorem of Pythagoras, the same as the Babylonian theorem of the same content. But there are different ways in which we present and those are determined by the cultural context in which the mathematics is done. That is the theme of what I wrote. Now, as far as Indian mathematics is concerned, if you look at the statement of, the example for me, the quintessential example for me is the theorem of the diagonal, because it's very simple, truly universal, appears to have been invented or discovered or imagined by several civilizations in slightly different forms. As far as the Indians are concerned, the two main ways in which it is stated, one is the Geometric Theorem, which says that the area of the square on the diagonal of a rectangle is the sum of the squares, sum of the areas of the squares on the two sides. The first formulation of this principle does not have any reference to triangles. It is reference to rectangles. That's not the way it is done everywhere. So there are these, and the reason I think is that there were very few triangular Vedis in the Vedic times. There were many rectangular Vedis or figures which are derived from a rectangle. So there is this question. Now, as far as Indian mathematics more generally is concerned, I think the biggest influence on it has been, biggest cultural or civilizational influence on it has been the extraordinary importance given to the spoken word in India in the beginning of our civilization, if it is defined by the presence of writing. So that weight has many consequences. One of them is that everything has to be given names, and numbers had to be given names. And one of my themes is that you can make the naming of numbers as precise, as contentful as the writing of the coefficients of the polynomial in a sequence. You can do everything you want to do. You can do everything with names as you can do with symbols. It's somewhat clumsier, but as effective. It had many other consequences. For example, the idea of infinity. I'm not going to say very much about zero. Zero is not very interesting in an oral civilization because you don't need it. You don't really need it. This point has been made before today. Infinity, on the other hand, is an extremely interesting object because you can't name an infinite sequence of numbers. You can see in the Taittiriya Samhita, for example, there are several passages in which you can see they're exploring how far can I go. And at the end, all these lists will end by saying, it'll begin by saying Ekasmai Swaha, it'll end by saying Sarvasmai Swaha, after getting up to 100, or in one case up to the 10 to the 19. So there is this very significant influence of our oral tradition on the way we did mathematics. For example, Bhaskaracharya, after he says that we should use the names of colors to denote unknown quantities, and saying also that we can work with the first syllable of these names, if you go through Bijaganita, for example, there is not a single problem stated or solved in that form. Everything is in narration. So it wasn't easy to get rid of this thing. At the end, Yukti Bhasha says, at one passage I'm very fond of, he said, so thus, by multiplying by 10, we can get to higher powers of the number you started with, higher higher powers of 10. However, since there is no end to the names of numbers, therefore there is no end to numbers. It is as though numbers existed because they had names. This is one aspect. The other things are, of course, it's been discussed a great deal in various, formally and informally in this meeting, the problem of proofs in Indian mathematics. I have one comment to make, which is that if they didn't have methods of validation which are entirely reliable, you would expect to find many wrong propositions in Indian mathematics. There are very few. Offhand, I can think of only two. And both of them are due to one of the greatest of them, Aryabhata. The volume of the sphere and the volume of the tetrahedron. They're both wrong. Okay. There are no other mistakes. And these are wrong in a very trivial sense. That is to say, he got the power right, he got the coefficient wrong, because he probably reasoned by analogy. So proofs existed, but not proofs in the accepted modern Western axiomatic deductive method. But that, of course, is not an argument against Indian proofs, because people surely have read Imre Lakatos' Proofs and Refutations. That is a critique of the deductive system of the example given there, the object to which it is connected is the Euler characteristic for polyhedra. And the conclusion is, ultimately, proof is, that's not the way you will find it in the text. The proof is, proving a mathematical proposition is a matter of consensus. And Nilakantha says very clearly, there are steps to be, in fact, some of the steps that Lakatos takes in his discussion of this question are uncannily parallel to what Nilakantha said, for example, in Jyotirmimamsa. So proofs are, I think, up in the air. It's something which, there's also the question of in which direction will future work go. I think one of them will be to formalize methods of proof which are not strictly deductive axiomatic. That's my second point. Then the last is, what is not Indian in Indian mathematics? Can we see cultural currents flowing into Indian mathematics and cultural currents flowing out of Indian mathematics to other mathematical cultures? This is a question which is quite not settled at all, because proofs of this kind of thing, that is, I don't want to use the word proof, solid evidence for this kind of cultural cross currents will come by combining many different things, like, for example, of course, temporal priority, then a possible method of contact, possible means of contact, then the invariant mathematical DNA, including the mutations from one civilization to another. So that's a very difficult problem, and many of us are concerned with this question. We have many things to say about this, but I think it will be something which will take more and more the center stage in the future of this kind of discussion. These are the three themes that I want to highlight from my own point of view, or from my own interest in this subject. Okay.
Thank you very much, Professor Divakaran. I think we'll pass the mic in the order you are seated. So, Professor Kim Plofker.
Thank you very much. Just one point, I have forgotten now, how much time do you recommend to speak now? We do, great. I think I have just 2 points to follow up on those excellent remarks there. First of all, I think Professor Divakaran makes a very good point about the content of mathematics being equally true, whatever culture it appears in, but it is not just the presentation, but the selection of topics that varies from one culture to another and relates to the methodology and the philosophy involved in mathematics. For example, one of the things that we see in Indian mathematics that we don't see in Greek, and this relates to your point about proofs, is a great freedom in addressing certain types of problems that were dealt with only very late in Western mathematics. For example, We have, when it comes to various types of estimation or approximation, particularly iterative methods in Greek mathematics, very rudimentary and procedures, if any, a great theoretical neglect of it, because we have in classical Euclidean tradition a very restrictive approach to rigorous proof that is very closely tied to geometric diagrams. It is very difficult to draw a diagram of an iterative procedure. There is a dynamism in the process that you can't put in a static figure, and there is similarly for an approximation method, you cannot get a rigorous geometric proof of something that is gives you an approximate result. But when you aren't limited by that approach to truth, solution, and validation, then you have the freedom, as we see in the Indian texts, to it creates a number of topics in mathematics that we don't see elsewhere. And this is related to what Professor Datta was saying yesterday about the arithmetic mean as a form of, part of a process of estimation. Similarly, there are things that we see in non-Indian mathematics, such as the Greek number theoretical concern with primality, that don't appear until late in Indian texts. The Indian texts are very concerned with issues of divisibility, rationality, as we've seen with the solutions of indeterminate equations, but the concept of the prime number and the properties of a prime number, or of all prime numbers as a member of a particular category, that doesn't show up. So I would say, what is Indian about Indian mathematics can't really be answered except by the entire corpus of the discipline itself. So, thousands of years of texts. But, insofar as I can summarize that in 3 minutes, that's what I would say.
Thank you. Amartya?
Yes, first of all, I agree with all the points that Professor Divakaran has said just now, and things which he has not said now but had said earlier. For instance, some of the things which are actually Professor Divakaran's point, that the recursive character of Indian mathematics, it has not been so much talked about. He has elaborated it, not today, but on earlier occasions. This is something which I would remind. And just as a supplement to what he was saying. So mathematics is universal, but there have been certain cultures which have laid emphasis, which now have become universal, like this axiomatic approach. This is standard mathematics, which have originated from Greeks. My feeling is this algorithmic approach of mathematics. In fact, even the word algorithm has its genesis in, has the etymological roots in the Indian mathematics. So the algorithmic approach to non-trivial mathematics, that my feeling is that it is something Indian. And this is some, and if you look at the Sulva mathematics, it's constructive character of the Sulva mathematics, Sulva geometry, which Professor Divakaran was mentioning, that and this algorithmic nature, these are probably related. And another point I would like to say, something characteristic of recent mathematics, is this what is called algebraization, and of which coordinate geometry, which is not Indian, is an example. Now, this algebraization was a feature, an early feature. I do not know how much it got transmitted, but this may not be exclusively Indian, but there was certainly, not only there was algebra, but this algebraization, for instance, the trigonometry, the way trigonometry is geometry of triangles, but the way it is treated, it looks like a subject in algebra. And that character is Indian. Another aspect which I notice is the counting. What is this combinatorial? And my knowledge about the other civilizations, frankly, is second-hand. But then those who have written about roots of combinatorics, the experts in combinatorics, they tend to acknowledge that this Indian tendency of building up big things from small blocks, that explains these early occurrences of combinatorics in India. So this is something which could be looked at, the history of combinatorics, which this building up, I mean, which you can see in like Panini's grammar, that building up something from these elements. So that is one thing. Now, regarding the decimal system, again, as a supplement to what Professor Divakaran was saying, the importance of the spoken language. Now, there is I mean, those who write on the history of this decimal system, there is an emphasis on the decimal notation to the exclusion of everything else. It is as if the decimal, as long as it is not the notation, I don't recognize anything else. And this has led to an undermining of the importance of the oral tradition, the oral aspect of the decimal system, which of course doesn't have the zero, but it encapsulates many profound aspects of the decimal system, which gets missed out. And this is a serious loss, that this decimal system, its mathematical aspects, has been hijacked by the zero. So this, so what I would suggest is to take this aspect of the importance of the spoken language, the naming of numbers, more seriously, and some kind of mathematics is not usually presented in isolation, but as a part of a general culture. And like, for example, the way Bhaskaracharya presents things, that's a classic example, the way he introduces infinity. You all know what I'm talking about. And this could, this aspect maybe has to be looked into, because something like infinity occurring in Indian mathematics early and very seriously, and also this division by zero, which has to be properly understood. This may have something to do with the fact that infinity is occurring in the cultural, I mean the non-mathematical thing, quite early. So the rigor that we have in mathematics and the tendency to strip it of all its other associations may not be right in understanding the evolution or possible things, and even this evolution of algebra. This may have something to do with the symbolism which is there in the Indian culture. For example, the Vedic literature, expressing something which cannot be expressed through imagery. That's not the notational symbol, but this tendency could have an impact in the early occurrence of this algebra. Now, finally, regarding proofs and formalism, many things have been said and will be said, so I am not going to that, but just I like to remind you that this so-called lack of proofs, there is a stage in a subject which is not empirical. So here I'm not talking about Indian mathematics, I'm talking about any branch of mathematics, particularly non-algebraic. There is a stage in its evolution where you have theorems are coming first, and then you develop the language necessary to have it on proper footing. Now, the geometry in the Western tradition, the earliest text that we get is the Euclid's Elements, when things have crossed that initial discovery, wherever the results were discovered, and had come to a stage when it could be axiomatized. And the Sulver tradition is a remnant of a tradition which is much earlier. Now, I'm giving an analogy. This is from modern mathematics, some subject called topology. Nobody credits the Eilenberg to be the founder of topology who gives the axioms, and nobody denies that Poincaré had theorems. So this topology, the vision comes first, the deep theorems came first, and much later it was axiomatized. Now, this is an aspect which has to be looked at, and Poincaré had proofs, but the proofs are not expressed in the way it is done now in this post-Eilenberg era, and efforts were needed to develop a language where the theorems could be expressed. But the Poincaré's theorems are not considered empirical. So these theorems in the pre-Euclidean thing has to be also looked at from that aspect. This is Poincaré's topology is not something Indian, but maybe there is something to be seen about Baudin's treatment of Pythagoras' theorem and Poincaré's treatment of theorems in topology vis-a-vis Eilenberg and Euclid. And maybe
though the content may be same, the thought processes that have gone in could be in different directions in order to arrive at the result. The language which has been employed is very different, in using which the content that is there in your mind has been explained to the other. And the kind of problems that have been attempted also varies. The nature by which you try to convince yourself regarding the truth of a statement also varies. These are the four aspects. The nature by which you try to convince the truth of a statement, which is generally referred to by the term proof, has been referred to by the term vasana here, primarily. Maybe Professor Srinivas, who has been writing on this, may explain further. But the point I wanted to drive here is the very word vasana communicates what he wants to convey. So the word springs from vasu. Vasu means to stay. So vasana is a certain process by which you are able to transfer the knowledge to the other person that it stays with him. So if you just quote something and then you move away, then it doesn't stay with you. So vasyate yena, so tad vasana. Yes, gets established firmly and remains in your mind. That is more important. Okay, so this vasana, see, the one general thing that we find in the Indian mathematical texts is, so starting from Aryabhata to Ganita Kaumudi, which Professor Divakaran was also alluding to as a beautiful text by Narayana Pandita, we find primarily the topics that are discussed are of relevance in our day-to-day activities. Most of the topics. So there will be a special chapter in Khata Vyavahara, this, that, etc. Most of them are related to that. Now, it's not that every aspect which they touch upon will be able to, you will be able to link to your day-to-day things. But the point is, you will be able to deal with most of the things that you have to do in your transaction. That is what I was trying to refer to. Vyavahara hetoho. Loka Vyavahara has been the primary objective in developing mathematics. So as far as the Indian tradition is concerned, And this Vyavahara Loka doesn't exclude problems like solving in astronomy. So they may not be directly connected to Loka Vyavahara, which the vegetable vendor does with you. But they are indirectly connected as to when this festival has to be celebrated. You have to do computation, for which you need to do various things, and those are also included in that Vyavahara itself. So Vyavahara can be Loka Vyavahara, or it can be Shastra Vyavahara. It can be, so it is primarily related to that, not some other thing. Okay. Then this thing, it just struck me when people were referring to this infinity. So in one instance in Vedic passage, so he was saying Sarvasmai Swaha. So there, so when they wanted to offer venerations to a particular deity, they start with Sakritte Agne Namaha, Dviste Namaha, Triste Namaha, and so on, it just goes on. Then he finally says, Aparimita Krutvaste Namaha. So Parimita is limited, Aparimita is unlimited. So that is what we basically refer to by the term. So Bhuma. So Aparimita Krutvaste Namaha. This is a way of expressing. So then, of course, the other thing which I want to point out here with reference to Indian mathematics is, so the way I look at and the way I have looked into some of these texts sort of clearly indicate that a very conscious effort has been made in coining the terms. So this is not generally applicable to various things. So this is very specifically, if you look at either astronomical texts or mathematical texts, so whenever they try to coin, this is a general attempt which has been made in Sanskrit literature, and that gets reflected in this also, because we have a very specific discipline which is called Nirukta. So you try to arrive at all the nouns based on the verbs. So that is the idea. So initially we start, our language skills starts from verbs. So you try to coin a word in such a way that you will be able to convey the idea. So the one example is Vasana, which I gave, and you will find n number of examples which one may be able to quote in the Indian text. So the attempt has been to introduce a new term, so by trying to coin words which will be easily retained in your mind and you may be able to link into. So that is another aspect. And of course, these things, in fact, so he was referring to this algebra. So there has been a very clear understanding that this forms the basis of arithmetic. In fact, the entire Vedic mathematics, so whatever 16 sutras, so lies on algebraic principles to employ, to do arithmetic. So the arithmetic process, so has a certain algebraic principle behind it, starting from square root, starting from cube root, starting from various things. And this has been so beautifully conveyed by Bhaskaracharya in two different contexts. So I'll just quote one thing and then I will pass on the mic. So he says, Utpadakam yat pravadanti santaha adhishtitam sat purushena sankhyaha vyaktasya kritsnasya tadeka bijam avyaktamisham ganitancha vande. There is a lot of beauty in this verse, that apart. It can be interpreted in three ways. But the point is, so there has been a very clear understanding that algebra so forms the basis of arithmetic. So vyaktasya kritsnasya tadeka bijam. So the word which is used to refer to algebra is bija, bija ganitam. So vyaktasya means so that which is evident, so tangible. Tad eka bijam, so the avyakta, so forms the basis for this vyakta ganita. So in some sense he is trying to convey, and it is conveyed elsewhere also. So bijam matihi. See, so bijam matihi. So in fact that is something which is so beautifully conveyed. So maybe I can elaborate later. So I'll pass on.
So Professor Srinivas and I have the privilege of sitting right down the end when all the points that we've written down have basically been covered by the last four speakers. But I do think I have a couple left which are new and can build upon what the speakers have said so far. And the first thing I want to remark on is the word Indian, and of course, being from outside of the culture, what does India actually mean? Is something that interests me and keeps me awake at night. And perhaps even recently, just in the last few days, was really impressed upon me when we were visiting this most beautiful manuscript archive in Pondicherry, which there are some 7,000 or 8,000 manuscripts, and they're all in Tamil. So what do we mean by Indian? All of the talks, or almost all of the talks today, have been concentrating on, high forms of mathematics that are expressed in Sanskrit Siddhantas, which are absolutely beautiful and worthy of study. But there's a whole, and we feel, all of us, that there are lifetimes of work to be done just in looking at the Sanskrit tradition. But then you open the field even more. And what else is India? Well, of course, there are all the vernacular traditions, the stuff that's done in Tamil, the more everyday stuff, Karnataka. There's manuscripts in Malayalam, which may be written in Malayalam, but are in Sanskrit, or there are Malayalam manuscripts. So we're really talking about an incredibly rich tradition beyond just the Sanskrit tradition that many of us are doing our best to try and cover in our lifetime, that is. So I would really make a plea for what is Indian about Indian mathematics is not just the Sanskrit texts, although they are prime importance, but also the incredibly rich and varied vernacular traditions that are both connected in both direct and nuanced ways to the Sanskrit tradition that is perhaps more central. So along that tradition, many of you, and something that I really admire, particularly living in a a sea-locked country like New Zealand, is that many of you speak more than 2 or 3 languages. You'll have your mother tongue, you'll have English, you'll have Hindi, or the various languages that surround you on this very rich and diverse continent. Some of you will have private libraries or manuscript libraries or access to manuscript libraries. These are very important to getting an understanding of what is India beyond some of the more, scan them, upload them to repositories, make them available, preserve them, protect them. So that's what I'd like to say about India. The other thing I would like to say is what's Indian about Indian mathematics, and it's also a question of where do we find mathematics, but more in a philosophical sense, and this point has been touched upon before, is that for other cultures of inquiry, such as Greece, and other famous ones, mathematics really is the paragon of intellectual thought. It has a very epistemologically privileged place, and that's largely thanks to philosophers such as Plato and Aristotle, for whom mathematics was really a paradigm for intellection more generally. However, in India, there's this beautiful contrast between this sort of epistemologically privileged place that mathematics has. In India, some would say that grammar instead supplants mathematics in this case. Grammar is really the key to everything. It's where we start when we're analysing the language. The language is the starting point. That is, and mathematics sort of falls underneath that. So a lot of the times when outsiders or more general historians of mathematics are looking for mathematics, they don't know where to start looking, or they won't look in places where you expect to find, these underlying rich and deep, profound mathematical concepts, such as in grammatical texts like Panini and the like. So we must be very careful, of course. What's beautifully Indian about Indian mathematics is that you will find key mathematical thought processes in places where we are least likely to expect it. Therein lies what is very distinctly Indian, I think, about Indian mathematics. Thank you.
Professor Divakaran has opened a hornet's nest by asking this very provocative question: what is Indian about Indian mathematics? A lot has been said, so I would like to sort of take it into a different kind of a plane. So essentially, is it meaningful at all to talk about Indian mathematics? Would be one kind of an issue. Is it meaningful to talk about Indian civilization? Civilizations, are there several civilizations? They have all various common features. So would it be meaningful to talk about, except for a certain geographical identity, or do civilizations have some characteristics? Perhaps most scholars will agree civilizations have different characteristics, so it will not be debated as a meaningful question. But when it comes to science, when it comes to mathematics, so the starting point, we say it's universal, that the discoveries of science, that theorems of mathematics are universally valid. And so what does it mean to talk of Chinese science or Islamic science or Greek science even? Now, I mean, so as of today, the modern world of today for the last 2-3 centuries, we perhaps seem to be practicing, there's a large community which is not nation-specific or civilization-specific, which is interacting and building upon the sort of corpus of knowledge and ideas. And the discourse is cross-civilizational in that sense. We may not be contributing as much to this progress of this knowledge. The centers of this knowledge may not be located in the Indian region, but we are part of a larger thing. And perhaps it's not very meaningful to speak of what would be Indian mathematics in the 20th century. In fact, I remember a joke of Professor S. Varadarajan. When he built this beautiful building of Indian National Science Academy, he took people around and said, look, there's nothing Indian or national about this Indian National Science Academy. I mean, he could have added nothing scientific or academic also to it. Now, anyway, jokes apart, I mean, till about 200, 300 years ago, practice of knowledge was not like this. This most historians would agree. And the books that the Keralite astronomers would have read, or Neela astronomers or whatever, would have read, wouldn't be Euclid or wouldn't be Tadhikara, they wouldn't be the 9 chapters. So they would have built upon a certain tradition. So in that sense, there were distinct scientific, mathematical, technological, philosophical, even traditions of political thought, etc., which built upon certain corpus of knowledge. And in fact, they were written in certain languages, that the Greek science was written in Greek language, even in the Hellenistic Roman period. They were sitting in Algeria, they were sitting in Libya, they were sitting perhaps in Syria, and they were writing in Greece and communicating. At later period, it became Latin, as far as Europe was concerned. Islamic science, whether it was written even in Morocco or or in Palestine or in Iran, though Persian was a very highly civilized language, was mostly done in Arabic. And in India, even Kerala astronomers, when they wanted to communicate with the trans-Indian Jyotish Shastra, they would use Bhuta Sankhya and not Katapayadi and write in Sanskrit. So there would be communication, there's a community of discourse within a civilization in which this knowledge developed. But now, does that mean that these sciences were actually different? Does that mean that this mathematics was actually different? Is the question we are asking them. But we have to grant that the civilizations had a certain internal autonomy. It didn't mean that they didn't interact. I mean, we know that Islamic science developed by first a large amount of translation from the Indian corpus and later on from the Greek and the Hellenistic corpus. And we know that they did build a science in Arabic, they did build a tradition of their own after having taken everything from them. And there was an internal discourse between Al-Ghazali and Ibn Sina, which would have nothing to do with whatever discourse was between Aristotle and Plato. So we might have borrowed, as Divakaran says, entire astronomy from Ptolemy, but what Aryabhatta was writing and then what Brahmagupta was writing and later on what later scholars wrote, they did not have to look into Ptolemy, they didn't have to look into the other Greek scholars or even the later works. So there is an internal discourse even when there is borrowing. I mean, the Indian place value system has been borrowed, or some ideas of algebra have been borrowed, they have been transmitted across. But they have been internalized into their own civilizational traditions. And later on, what is written in Liber Abaci will have nothing to do with what, directly, it will have nothing to do with what is written in Ganita Sarasangraha. Only some great scholars who will do some dissection of these books will try to see the same problem in some other manner, the same idea in some other manner. So, there is an internal coherence and consistency. And when it comes to India, we modern Indians have a certain problem that there are so many subcultures in India which were also as ebullient, as creative, as dynamic as a trans-Indian Sanskritic culture, that we have books in Tamil, Telugu dating back to 8th century or even earlier, or a very vibrant Malayalam sort of technical literature, something which sort of the European civilization did not see till about late 16th century when Bombelli or Galileo started writing in Italian. But even till the time of Gauss, Latin was the language in which everything was written. Most of the things were written. So in India, we have a vibrant local culture. So sometimes confusions occur. In fact, 60 years ago, I remember Nagibai wrote a paper called Tamil Astronomy. What he was referring to was the astronomical methods described in a book called Kala Sankalita, written by John Warren in 1825, which actually refers to what is called the Vakya system of astronomy, which of course the Europeans first discovered when Lejeantil came to Pondicherry in 18th century. Now, much later, in 1961, the first Sanskrit text of the Vakya system was published by Upana Shastri and K.V. Sharma. And today we will look at the other Vakya text which Uttamana Somyaji wrote in 17th century. There is nothing Tamil about it. I mean, there is something South Indian about it in the sense that this Vakya system did not cross South India, much of South India, but entire South India practices this Vakya system. So, if sort of a trans-Indian scientific discipline got disturbed at some stage, it wouldn't be because the civilizational discourse within the trans-Indian region got cut and they diverged. It is because of certain social, political circumstances when this civilizational discourse was not easy. There would have been times when that was the situation in Europe, that the calculus in England got left behind by a couple of centuries because of Newton's great antagonism with Leibniz, and the British scholars refused to follow the calculus of Leibniz. And so these kind of instances, there will always be there. So in India, we have a special problem about talking about is there an Indian way or not an Indian way. Surely there will be several sub-Indian ways. But there is also something called an Indian way, which distinguishes it from the Chinese way or the West Asian way or the Greco-European way. But now, what are its distinctive characters is the final question. I mean, that we do know that science as practiced till about 200 years ago, mathematics as practiced about 200 years ago, was civilizational. But now, what are the civilizational characteristics? Now, that's where I think we would have to go to the second question of Michel, because we really do not know enough about Indian science to be able to sort of assertively, systematically talk about what are distinctively Indian. Europeans have studied the last 3 centuries. Great scholars have looked into all Greek texts, and to some extent they have looked into the Chinese and Islamic and Indian texts also. And they have made certain characterizations of what constitutes Greek mathematics as distinct from Chinese mathematics, or what constitutes the Chinese technology as distinct from. So these have been studied. But about India, the amount of the gaps are tremendous, and each time when we study something, we will discover something new, some new characteristic, some new idea. I mean, what was said at the time of David Eugene Smith when he wrote the history of mathematics in 1900 is very different from what Victor Katz is writing in 2007 about the history of mathematics, various chapters on what is Chinese mathematics, what is Indian mathematics. So I don't want to, in fact, I have taken too much of your time. So I don't want to go into the specific characteristics of what is Indian. All of our panelists have recounted many interesting features of which characterize the way Indians have practiced mathematics. So I just try to argue for you that it's a genuine question to ask what is Indian about Indian mathematics or Indian about Indian science. And this was a very meaningful question, at least as regards the practice of science, till about 200-300 years ago. It may not be a very meaningful question in the way science is practiced today, but even today I think French mathematics differs very greatly from the British mathematics or the American mathematics. These very serious mathematicians will know in some manner, and they will be talking that the Russian school. And finally, just a word about this axiomatization. That's a very important point of Amartya, that axiomatization always comes at the end of the development of a subject. I mean, if somebody read the history of probability theory, from the time of the letters of Fermat to Pascal, to the time in 1931 when Kolmogorov wrote the axioms for probability theory. And unfortunately, Kolmogorov was right at systematizing the discipline exactly when the discipline lost its meaning in physical sciences. Physicists had moved away from the Kolmogorovian kind of probability theory. The quantum theory demanded a different probabilistic framework, which could not be accommodated, and the basic framework was written by von Neumann about 4 years before Kolmogorov's axiomatization of classical probability was done. In fact, quantum probability precedes the Kolmogorovian probability in that sense. But this is what happens. So axiomatization, most of what is contained in Euclid's book, people speculate from 50 to 80%, belongs to geometric ideas and results that were known from 1,500 years earlier in Egypt and Babylon and in Greece itself. Maybe many of the proofs were Euclid's because he is systematizing them, just as many of the proofs in Bourbaki's books will be their own because they are systematizing whole of analysis. They may not be following Cauchy's proof. What Indians did, they did not practice axiomatic mathematics. They practiced deductive mathematics. They deduced from known things to unknown, but they refused to, for all time, write down a system for various reasons which we could discuss. But that did not reduce the logical rigor of Indian mathematics, but the tendency of Indian mathematicians not to use the reductio ad absurdum method of argument also further sort of is in the context of refusing to make an axiomatic system. So this, we could discuss these issues specifically, but crucially, it's a very meaningful question that Professor Divakaran has raised, and I'm sorry I have taken too much.
Thank you very much. We have already quite a wealth of answers, and there is, I think, a book waiting to compile all these answers together and develop them further. But meantime, may I invite the audience to react and put questions? Yes, Madhumita.
Thank you so much. What a wonderful panel discussion on the issue of the Indianness of Indian mathematics. Pardon my profound ignorance at the very outset, but I'm really curious. So one, it is very heartening to hear that the culture by which we understand as the way of life precedes mathematical imagination and philosophy, which then gets translated and it gets the formula, a precise format, form, numbers, precision, etc. So culture preceding philosophy and philosophy preceding this precision is very heartening to know. But this is something which I assume, as Professor here has very correctly pointed out, in very different cultural contexts. And therefore, I think it makes sense to look at the different contexts within which mathematical imagination originated, and to look at the circulation of ideas and the cross-fertilization. And I think a panel, a theme like the Indianness of Indian mathematics would become more meaningful if we look at this, study it across civilizations, across various domains, texts, and so on. So this is just, as a historian, I feel that it would make it more meaningful for us to understand, and what is this Indian thing that we are talking about when we talk about the mathematical imagination and philosophy, which would originate in in a very similar manner, in different cultural contexts. The other, while on this subject, my question to Professor Subramaniam is, when you talk about the bija in the verse that you just referred and you interpret it as algebra, so I would be very interested in knowing how profound would be the algebraic insights that you can derive from a verse which talks about bija in this manner. I mean, how far can you really take this? And what kind of theory would you be able to build from from the mere mention of a bija? I do not know if there are further insights in other verses. For instance, can you build an entire theory and say, here is algebra which originated in India? You know, how far can you take this theory? I mean, I would be very keen to know.
All right, so we'll.
It's okay. To Professor Amatta. So you said that there was the culture of, what they call it, deductive proof or the computational proofs, right? So there are the techniques leading to, let us say, calculation of square root of a positive integer. And then when we teach this to school kids, we actually teach this algorithm that start doing this, continue for 10 steps, 12 steps, 15 steps, depending on up to what decimal place you want the precision for, and then stop. This is going to give you the answer. But still the question remains that what you get, whether it is actually a square root or not. Right. So my question is whether such issues were addressed. I quite understand. I'm saying that one could give an algorithm which leads to the correct answer, but this whole sense of correctness, whether that was there in those verses or whether this is a kind of our understanding and interpretation.
I'll try and be brief. Thank you very much for this great panel. It's a complicated set of thoughts that I have in mind. I won't go into all of that. But when we are talking about this question, what is Indian about Indian mathematics, it's also a question that gets us to epistemology. It's a question about mathematical episteme as an object that circulates around the world. Now, what kind of model could we think about this circulation of knowledge? Because again, to go back to my particular interest in literary studies, one of the things that I'm interested in is how we could think about something like global modernisms. And one of the ways in which that particular circulation of knowledge has been conceptualized is through a model of coevality, not necessarily temporal priority and that particular linear temporality, but a certain kind of coevality. Now, correct me if I'm wrong, but one thread that kind of ran through quite a few presentations that I have witnessed in this conference seems to have a very strong emphasis on this logic of temporal priority. And I'm wondering whether to a certain extent we could, if I may provoke, we could see this as a post-colonial empire writing back to the mathematical episteme of the West.
Rhetoric and discourse.
I will not venture, but I'm sure our panelists will be able to. Any other comments, or shall we first, Raj?
So it's a great question. What is Indian mathematics? I don't know either. But one theme which came out is it's the way of thinking, the way of presenting, either by poetry or by any other means. Okay, that was the beauty of the history of mathematics. And when you all talked about Indian text, you must be referring to circa 1800 textbooks. That's what you're telling us, that how mathematics was presented. Nowadays, modern mathematics is not presented that way. So we lost the tradition. If history is supposed to teach us something, that we should learn from the history, the good things about history, and our whole education system is westernized. None of our historical Indian way of teaching exists. You can't even see. I can't even find a textbook you guys are talking about in general's bookstores or in any curriculum. I don't know where you're finding it. Maybe you're living in the past.
We live in the present, dealing with the past.
So I think we should first try to address these questions. Kim, would you like to? Yes.
I can just make a quick remark with regard to the temporal priority issue. It's an interesting question about how colonialism plays into that, but certainly it is a common feature of mathematics in general. We are influenced not just by talking about Indian mathematics, but by coming from the culture of mathematics in which priority of finding or proving a result has become, one of the major credentialing issues. So, of course, as historians, that isn't or shouldn't be the most important problem, but as historians talking about and to and with mathematicians, it remains very central. So just throwing that out there.
No, I'm full of hope in the sense that we are not searching for something lost forever. The tradition of mathematics lives. There have always been gaps in the Indian. For example, from the Silva Sutra of Apastamba and Baudhayana till the next real breakthrough, there was a very long gap. Let's say Pingala is the next really creative mathematician India has produced. In between, what did he have? We had the search for larger and larger numbers. That's about it. Now, between the disappearance of the Nila school with, let's say, Nilakantha or Jeshtadeva and the arrival of Ramanujan, there's only been 350 years. It's not a big period. And in any case, every time there was a rejuvenation, there has been very, very strong inputs from outside the system. For example, Aryabhatta definitely was inspired by the Greek mathematical models of astronomy. There is no doubt about it. Kerala was stagnant before Madhava came there with new knowledge, new spirit. So I'm full of hope. I'm not searching for something gone, lost, something lost. I'm looking at something, I think, which is living, very much so. Second point is, there is a model for looking at mathematics as part of the universal culture, which we all are part of. There is a model. That model is the comparative linguistic studies. Languages, we now know, they don't have too many independent roots. For example, Indo-European family is enormous, very large number of languages. How did we get to understand this? Began with William Jones at the end of the 18th century, and it became a flood of scholarship of various kinds in the middle of the 19th century, along which Panini was discovered by the Europeans, and they contributed enormously to the understanding of Panini. I think it's going to happen again. I think these currents will flow, and I think we should keep this in mind, this model. It's not for, it's not just commonality of words which define the Indo-European family. It is the structure that defines the Indo-European family. So I think we should have a new science of comparative mathematical studies, historical studies, and I think it will be a very, very productive enterprise. That's what I feel.
Okay, I think this question was directed to me. This a plus b whole square. I'm not a plus b. Computing the square root. So, there are various aspects to it. As far as justifying, this particular example, as far as this culture of justification of an algorithm or an identity, that is certainly there. That, as Professor M.D. Srinivas repeatedly emphasizes, that we tend not to look at the commentaries, we tend to pick up the masters. And this is a general tradition not only in Indian mathematics, but in all the branches of science, that there are some texts which give you the gist, the essence. Because, see, it was very difficult to preserve the knowledge that this transmitting mediums, it is either through memory or, these perishable palm leaves. So there have to be some texts which would give you the essence of the knowledge. Like in Ayurvedic text, you have the principles. The methods are transmitted orally, but some texts talk about the method. So similarly, in mathematics, there are some commentaries which elaborates and which have a tendency of giving justification, but probably not everything was justified because the process of describing it would be too complicated. So I am not aware as far as specific example of square root is concerned, because it is not that I have looked at all the commentaries. I do not recall whether Bhaskara one has justified it. I don't know specifically for this example. Now, but the question is that did they know a justification? The very nature of the algorithm is such that the person who invented it could not have invented it as by trial and error that this works. It is inbuilt in the algorithm that the proof was known. So it is not, this statement is not something like a geometric or topological statement where maybe you observe a pattern and then declare something without knowing whether it is true. It's something like a conjecture. This is something which could not have been done, this very algorithm, without knowing, this a plus b whole square, etc., and all the things which are inbuilt into it. That is gone there. The person who is learning it may not realize why it works, but the person who is declaring it for the first time knew it. It is same with the Pythagoras theorem in as far as the Bodleian, that entire corpus is concerned. This validation of the validity of the, without the knowing of the validity of the theorem, the person could not have given the construction of the sum of the how to construct I mean even an easier one, that
transformation of a rectangle into
no, that is complicated. Sum of two squares. The sum of two squares, that is, take two squares of length a and b, then construct a square whose area is sum of the two given squares. Now they give the description, you draw the diagram, that gives a proof. Nothing else is needed. So the person who thought of that obviously knew the proof, although it is not described there. Now, as a continuation, when I was talking about, so here I'm going a little away from the topic, that what is Indian about Indian mathematics, and I would rather draw a caveat about something which is characterized as Indian mathematics, but which may not be that Indian. It may be a feature of mathematics. This is regarding this justification proof that etc. That in certain areas, thinking too far ahead of time would lead to problem, as you saw in the earlier film, in yesterday's film, that comparing Ramanujan with Newton, it is quite significant that what is happening is that this Ramanujan is stating results which at that point of time, and he doesn't have patience with justification. Now you think of the power series in algebra, formal power series that was given by Newton, and he freely computed with it. I'm specifically giving the name of, because Newton's name came up. And Newton is identified with, hardcore modern European mathematics. The later mathematicians, the real giants, Cauchy and Abel, they criticized Newton for dealing with power series which are not convergent. And later, much later, it was shown that Newton was right after all. Now, Newton didn't wait for the formal justification, for this, completion and all this, this Hensel and whatever they did later. He didn't, mathematics would have stagnated, so he just went ahead with.
Calculus might never have been invented before. This was not that.
Which one?
This regardless of the dependent of Newton limits, etc.
Yeah.
Calculus would
No,
never.
I'm saying that even within something, calculus is known to be or roots are known to be non-rigorous. But I said that except for algebra, so I withdraw that. That even within hardcore algebra, the standard of rigor, so calculus is known to be something non-rigorous at its root. So I'm just leaving that aside. But even something which is associated with purity of mathematics, that is algebra. So even there, that formal power series operations were done before justification of that. Or something like a polynomial has n roots. What I mean is that a polynomial of degree n has n roots. People went ahead, I mean, not only Newton, Galois didn't know the proof that a polynomial of degree n has n roots.
It's not that whether idea and equation precedes the proof or proof precedes the proof. Definitely an equation precedes the proof.
I'm not talking about that, but the point is that I'm saying that what I'm trying to illustrate is that even within algebra, the standards of rigor varied with time, and the consensus about what has to be. So by the time of Galois, the necessity of proof is firmly established in the second phase of Western mathematics. So with calculus, this emphasis on rigor had slackened. But in the 19th century, it had certainly come back. And by the time of Galois, it was, meaning the necessity of proof was beyond dispute. But even then, this, what you call that, polynomial has n roots. This was, No, I'm not talking about the fundamental theorem of algebra. I'm saying arbitrary, because Galois is not working over C.
Solvability of the quintic was established by others. And Galois gave a
but that theory, I'm saying that by our today's standards, even, see, Galois was a very rigorous mathematician. That's why I'm illustrating his name. But even Galois assumed that a polynomial, this is not a polynomial over C, it's over an arbitrary field of characteristic 0. Galois assumed that a polynomial of degree n has n roots without proof. And didn't state it as a, see, you can have a conjecture, if this is true then. There was no if then. Just it is a, deal between the people that polynomial of degree n has n roots. It is only in 1880, much after Galois, the chronicler, first established that a polynomial has roots. The formal proof. So I'm saying that even in a subject like algebra, the standards of rigor in this modern mathematics varied with time. Now, this aspect has to be remembered, because we tend, when we discuss Indian mathematics, which is, we are of course talking about ancient mathematics. When we discuss ancient Indian mathematics, we somehow blank out completely the history of modern mathematics. I mean 19th century mathematics, 20th century mathematics, we blank out, except for Ramanujan, who is kind of treated as an, crackpot or whatever. But that kind of thing was done by others, in out and out rigorous mathematicians. They have skipped things. So, and had they not done that, mathematics would have been poorer. If Galois had not gone ahead with assuming, forget about Newton, even Galois, if he had not assumed that a polynomial has n roots, I mean, things would have been backward. So this aspect has to be kept in mind. I'm just specifically giving an example from algebra. Another point I would, completely different flavor. This is a supplement regarding presentation of mathematics. This Lilavati type of thing, which you get in older text also, Mahavir, etc., that is presenting mathematics beautifully in the form of problems, and which we also studied in school, not from Indian examples, but this culture of making math, I do not know whether how far it was prevalent in other things, because I read somewhere that this went to Europe from India, this presenting mathematics as part of inventing, situations, mixture problem, this problem, that problem, for illustrating this thing. So that I do not know how correct it is, but this I have read. I'm just saying.
Just very quickly, So pertaining to your question as well as the question which was posed by the other lady, we find certain constructions, even in Shula Sutra, as he was trying to point out, where we very clearly know that the prescription that is given would have never been prescribed unless this person algebraically worked out for himself. So otherwise, I mean, you just draw this line and then you draw a perpendicular, the perpendicular will give you this. So it doesn't in any way indicate that it would have been arrived at by some trick. So whether it is algebra, or it is arithmetic, or it is geometrical prescription in doing certain things. So one finds that a certain amount of algebra, arithmetic and geometry is involved to convince the truth of this before he prescribes. So that is what he meant by saying. And even with respect to cube root, you can straight away see that once you cube it, so you get the reverse process, and therefore that is what is prescribed. So the very prescription is indicative of the, because the way it is prescribed, naturally you can very easily see that it is the reverse process of this. So, and therefore that the answer that you get is a cube of it or square of it. And as far as the other question is concerned, so this, the very word bija is employed in several contexts. So in fact, even in philosophical discussion, so they ask this question, Atra kim bijam, prashnasya kim bijam, means what is the seed for the question that you are asking. So this actually means the crux which lies behind posing this question. There is some other thought process. So similarly, so what one finds is when he makes this statement, in fact there is a very categorically statement, bijam matihi. So the very crux of doing mathematics is that matihi, bijam means the algebraic principles are the fundamental to all this. So that is the kind of emphasis that has been given, and this emphasis is born out of a very thorough analysis of what is going on in various different fields. So that is how this is said. And the final statement is, in fact, this question, I was reminded as the discussion went on, when I went to the US Embassy for the first time, I met this officer. He was asking me, why are you going to US? I said, I'm going for a conference on astronomy. What are you going to talk on? I'm going to talk on Indian astronomy. The next question was, astronomy is astronomy, what is Indian astronomy? What is Indian about it? So this was in 2001, I vividly remember. Then I said, true, astronomy is astronomy, but the way it is practiced in Greece is very different from the way it was practiced in India, and therefore I would like to use the adjective Indian astronomy. So they had certain notions about that things have to be like this only, whereas we didn't have. So the another incidental point which I want to convey here is, so the relations, the truths, etc. that are being stated here, so they are treated on par with various other philosophies. Somebody was saying, black cat in a black room in a dark. So the point is, so these are all certain things which have been accepted as truths which will be employed by various people, and therefore, so it is not something which is to be brought out from some heaven. So that is the kind of philosophical background in which, so even the models that we construct, so they are all something which will be useful for certain things. So that is the way it has progressed.
So very quickly, just I heard your question quite differently to maybe everybody else, and that when you said, how did they know where they were right? Well, at least that's what I heard you asking, brought to mind actual computations, actual number. And in this age of big data now, it's something that we're becoming more increasingly obsessed with. And one of the huge repositories of Sanskrit mathematics and astronomy that is only just now being brought to light, which myself and Professor Kim Plofker are working on, are numerical tables, which are, of course, somewhat ubiquitous to our eyes and therefore not very interesting because they just remind us of Excel spreadsheets, but these are the direct product of hand computations of people carrying out these algorithms which are expressed in these beautiful verses in their abstract format. This is somebody actually taking that rule, sitting down with, on the ground or a piece of paper and computing it out. And from the answer that we get for, if somebody says, what's the square root of, 13,901, for instance, and they've given you an answer, there are a whole lot of assumptions that when we can reverse engineer the process they've used, given the answer that they've given, what level of precision are we comfortable in working in when we're dealing with data? What sort of rounding procedures are we using or are we comfortable with? All these things that we don't find expressed in the verses because they're not, we don't have enough room to memorize them, but they're fundamental to the heart of mathematics, and they're in these numerical tables which we can reconstruct when we look at the data. So when I heard your question, how did they know what they were right? I immediately think, let's look at the actual numerical computations, the implementations of these more abstract rules that we find in the form of numerical tables, and we have millions of entries from which to answer that question.
Some important comments have come. The first was a suggestion that, are we saying that there is culture which precedes philosophical speculation from which science arises? And issue is not that way. I think they all evolve together. I mean, there is an influence mutually between the culture, the philosophy, and the science, and they evolve together. It's not that as if some worldview is set for some time and then for the next 5,000 years, that civilization functions that way. Second is the question of this, why are we, most of the talks here indulged in certain assertions of temporal priority or certain claims of, there is a certain historical context we have to understand. If somebody read one of the greatest books on history of Indian mathematics is the book by Datta and Singh, which was written in 1935. But about a large portion of the book is sort of spent in sort of refuting various dismissive statements about Indian mathematics that were being made in the couple of decades prior to that by important people around. So it appeared as if, after all, he could have discussed history of Indian mathematics only. Why is he talking of? Today when we read it, the other people who had made all these negative comments, a gentleman called K. Nobody knows him, nobody will read his book. But if you read Datta's words, you are forced to know what K said and then what was the reputation. And so there's a certain historical context to the way this Kerala astronomy, till K.V. Sharma published many of these books until they were discussed, etc. The only available thing was what one Charles Fish wrote about 150 years ago. And then it was forgotten. So most of the general histories of mathematics, which were not written by really competent experts, but by generalists, like Maurice Klein wrote a book, which even in 1970s, published by Oxford University Press and all that. So they sort of say Indian mathematics died out in 11th century with Bhaskara, 12th century with Bhaskara. They didn't have argumentation, they didn't have logic, they were good at calculation. So what is happening is we are in a certain evolving discipline. And so somebody has to claim something new. He'll have to claim certain priority. He'll have to, even Divakaran, for his issue to be discussed, he has to put a provocative question that what is Indian about Indian mathematics? So we are all sitting and discussing it. If he had merely described to you what Indian mathematics was about, most of us would say, we know all that, Aryabhatta, Brahmagupta, this is all well known. So we are in an evolving discipline. That's what I'm repeatedly trying to say, that there is much more that needs to be understood about Indian mathematics, not only Indian, Chinese, Islamic, etc., in the pre-1800 world. And once we understand it, then we will be able to talk about issues in a coeval manner. Because there will be mutual accommodation of you excel in this, we excel in this, or you are seeking for this, we are seeking for this, or you by your own conditions have arrived at this issue. Before 19th century, cotton fabrics were not manufactured in Europe. And the great industrial revolution was about manufacturing cotton fabrics. And in 18th century, most of the cotton fabrics that were not only sold in Europe, but were exported for slave trade, were taken from India. So a certain context brings in certain new discoveries, and all these great discoveries of industrial revolution, modern scholars have identified with the the demand for producing attractive, good, smooth cotton fabrics with the kind of coloring that the Indian weavers were able to produce. And this Britain was able to produce between 1760 and 1790. And that was the end of Indian cotton textile industry, because Britain was also ruling India. Anyway, so that was about that. We will be in a position to talk on mutual equal terms when this knowledge has become much better understood. And lastly, just a small point about this epistemic nature of science and nature of proof. You see, much of epistemological discussion is held to rule out something. So when people were writing 100 years ago, they said Indians discovered a lot of results, but that's not mathematics, because unless you give proof, it's not mathematics. And to some extent, it could even have been said about Ramanujan at the time when he wrote all his notebooks. But if you read in 2012, when Bruce Byrne has summarized what he has found from Ramanujan's notebooks, he says in 1940, Hardy thought 2/3 of the results in his notebooks, which were done prior to his going to England, were results that were already known. Bruce Byrne says in 2012, after studying these notebooks for 30 years, that more than 2/3 were new at his time. And there are about 3,250 formulae that Ramanujan has written. And if properly interpreted, only 4 or 5 of them might turn out to be wrong. And Ramanujan, like Fermat, is notorious for not giving any proofs. In fact, Wallis wrote this Arithmetica Universalis, which Fermat criticized, saying that the proofs are non-rigorous. You should realize that proof is Fermat is one person who kept on saying proof is very important, but would not give any. And later on, it was proved that most of the results in Wallis' book, which were of course not rigorously proved, were confirmed over the next 100 years. So this is what happens many a times. But at a certain point, people say that Fermat at least recognized the need for a proof. So it's not like that. Everybody recognizes the need to justify the kind of claims for progress in knowledge. And in India, this whole Pramana Shastra, Pratyaksha, Anumana, Shabda, very old. So the standards are set, the discourse is, the questions are asked. Nobody is going to accept somebody's claim just like that in any tradition of science or mathematics. The standards may be different, they may vary. And this we will understand the moment we get to know the history of these sciences much better. Then our discourse will be much more reasoned, much more nuanced, less acerbic, less assertive, more harmonious. Thank you.